let's just start with a super simple example and go from there and see if you guys are successful students. So I'm going to save these for later so I can use them. And let's go with what I've been doing all day, 500, just like yesterday, 500 gram car, 1,000 gram car. 3 meters per second. There is a collision. During the collision, the 500 gram car ends up having a velocity this way of 0.5 meter per second. What is the resultant velocity of this car? Can you do this one? Let's see. It's not a particularly hard question. You do have to consider what direction is positive to do this right. Did you do that? Excellent. So 500 times 3 plus 0, that would be the initial momentum of the system. That is a 3 all day long. I don't know what you think it is. And after this, here's where you need to be careful. Right? That 0.5 has to be negative, bounces back. Momentum has direction. Plus my unknown velocity there. This good? So what do we actually get for an answer? 1.75. That's right. 1.75 meters per second. Could you tell me how much kinetic energy was lost? Like, could you do that? I mean, because that's a question aside to this. It's last unit. So either you know what to do when I ask that question, or you don't. So if you can, perform it. Tell me how much kinetic energy was lost, but I want my answer in joules. I'll give you 60 seconds before I pick on one of you. Look, I'm just asking how much kinetic energy is lost. The only way to do that is to know how much kinetic energy there was and how much kinetic energy there will be at the end. Anything moving has kinetic energy, so it looks like the kinetic energy of the system is 1/2 times 0.5 times 3 squared. Right? That's the starting kinetic energy, which I believe is, that's 9 divided by 4, 2.25 joules. Now, afterwards, both cars have kinetic energy. It doesn't really matter that one's moving one way and one's moving the other because the direction doesn't matter. We're talking about energy. So what are you giving you add all that up? I'm not doing that in my head. Hurry.
1.5937.
Say again.
1.5937.
That's good, 1.6. Now, this would still not be the answer. This is how much energy there was. This is how much energy there is. The amount of energy lost, you'd have to subtract those two, because that'd be the amount of energy that was lost during the collision, proving that this is an inelastic collision and trusting that this is the right answer to that. I'm trusting that that's what you get when you add those things up. So I think we should try more. I think we need some more. So we'll do another one. Riddle me this. What if this were a perfectly inelastic collision? What will be the velocity of the system after the collision? The important detail was that I said it was a perfectly inelastic collision. That means the two objects link together and therefore have a combined velocity. That's all you have to do here. But that means that I have my 500 times 3 is the initial momentum of the system because the other car has no momentum. After the collision, though, I have a single object of mass 1,500. This would be a perfectly inelastic collision. And this looks like it's going to be 1 meter per second after the collision. Before the collision occurred, what is the velocity of the center of mass? I told you how to do it yesterday. Again, these are all things from yesterday. You guys done yet? Do you know how to do it? Just need to know. Just trying to rehash stuff from yesterday. So can I assume it's a no? All right, so if I ask you for the velocity of the center of mass of the system, I will remind you that for the system, the momentum of the system is just the sum of the momentums. There's only 2 objects here, but this would be for as many objects as you have. But it's a vector sum. Now, that has to be equal to the mass of the system times the velocity of the center of mass. I was bringing this up because during a collision, there's individual momenta transferred from one object to another. But for the system, the momentum of the system doesn't change. So if you want to find the velocity center of mass, that's all you have to do, which, by the way, we've just done, right? This is going to be 500 times 3 plus 0 equals mass of system, 500, plus 1,000 times the velocity of center of mass. When they were joined together, they were one object. That velocity was the velocity of the center of mass. So the answer is 1. What if they had not joined together? What would be the velocity of the center of mass after the collision if they didn't join together? Oh, you hear nothing that I say. You really don't hear the words I say. They're said, and I know it's the end of the day, and you're sad, but it's still 1. Yeah. It won't change. I just said that. Unless there's an external force on your system, there might be momentum transferred from one object to another, but the motion of the center of mass doesn't change. So even in an inelastic collision or an elastic collision or a perfectly inelastic collision, the velocity of the center of mass of the system stays the same. That's the whole point. That the only way you can change the velocity of the center of mass is to have an external force act on your system. That is Newton's second law. So if there's no external force on your system, there is no change to the velocity of the center of mass. Because all of the collisions obey Newton's third law. They're all internal forces, they're not external. So once you've established that, velocity of center of mass never changes. Wow. There might need to be some crying. Set up an elastic collision. What would an elastic collision look like? Don't solve it. I don't have time for that. You'll be crying before the end of the math. But set it up. It's in your notes. Remember, in an elastic collision, there's a certain statement being made to you. They're telling you something about the collision. just like in a perfectly inelastic collision, they are telling you something. In all collisions, momentum is going to be conserved. In all collisions, momentum is conserved. That doesn't tell you enough. Right, we can't find V5 or V10 on their own. There's not enough information. But if I tell you it's elastic, I'm telling you that the kinetic energy is also conserved. So if I want to set it up, that's how I set it up. 2 equations with 2 unknowns. All of this was yesterday. Now, I'm not going to do this problem. As I found in the middle of 6th period, they just looked at me funny when I was saying, how would you solve this problem? You do understand this is just 2 equations with 2 unknowns, correct? Please say yes. They couldn't. But that's all it is. And you are supposed to be well equipped. More importantly, in this problem, like with most, there will probably be some simplifications you can make. Like divide the top one by 500. Right? Get rid of all the 1/2 and divide the bottom one by 0.5. Right? Still 2 equations and 2 unknowns. You're still going to have to do the work. But I'll give you a hint. It's a quadratic, correct? You see that it's a quadratic, right? The bottom ones, the unknowns, are squared. That makes it a quadratic by definition. Quadratics always have 2 solutions, right? One of your solutions is already known. Your initial conditions are one of your solutions. So this is a quadratic where you have one of the solutions. So when you get to the point in the quadratic when you could factor, know that you have a solution. Use it in your factoring. It will make your problem go faster. In fact, because we know that one of the answers has to be 0, solve for that one. Solve for V10 because you know it has to be 0, which means you'll only have one answer and you'll know it. If you understand math, you'll understand why I told you those things. Come on, mathletes. I have so many of you in this room. I don't want to talk about this stuff. This is the old stuff. This is yesterday. You ready to move on to today? I think we need to. You understand that you have to get this rock solid. Right? This is just a part. It's one of the things that was missing from yesterday is that we talked about only one-dimensional problems. Absolutely no reason why there couldn't be a 2-dimensional problem. In a 2-dimensional problem, the objects can be moving in 2 dimensions. So if we talk about a simple collision in 2 dimensions, where one object is at rest and the other is moving, like cue ball towards another ball on the table. Simple enough? Or even just a bowling ball and a single bowling pin. Right, that is a 2-dimensional collision if we're just looking at it from above. In that collision, there's going to be probably a 2-dimensional answer. Something where one of the objects is going to go in one direction and the other object's going to go in the other. How this happens depends on how the collision occurs. The masses of the 2 objects, how much energy is lost, all sorts of factors. Now, the math on this is going to be tough, but there are some things that we can do to simplify the mathematics that you should pay very close attention to. In a 2-dimensional collision, one of the things you will be able to do is break the problem up and study it in 2 dimensions. So make it 2 one-dimensional problems. For example, only one object was moving before the collision. So make that the positive x direction. If I make that the positive x direction, that means that there is no momentum in the y direction before the collision. So at time 0, my momentum is only in the x direction. It's whatever the mass of the red ball is and whatever its initial velocity is. But the momentum in the y direction is 0. What does that mean? Well, start looking at how you break this up. The red ball is going to have a horizontal momentum and a vertical momentum. The green ball is going to have a horizontal momentum and a vertical momentum. These 2 momenta have to be equal and opposite, because the y momentum was 0 before the collision. So the y momentum has to be 0 after the collision. I'm not saying this is easy, because this could be angle theta, this could be angle phi. This will be p red ball sine theta, and this will be p green ball sine phi. But they'll have to be equal and opposite. They will have to add up to be 0. And of course, this is going to be p red ball cosine theta. And this is going to be p green ball cosine phi. These 2 have to add up to be whatever the original momentum is. So although these are mathematically cumbersome, there are some clear things that you can work on right away to help you figure out what the momentum is after the collision. And still, the velocity of the center of mass never changed. It's whatever the velocity of the center of mass was before the collision, and lies along the x direction. It has to, because that was the direction of the velocity of the center of mass before the collision. So in these problems, conservation of momentum has to be obeyed. So some of this isn't so terrible. I'm not going to be worried too much about a 2-dimensional collision. I would like you to be able to describe one, maybe pick one out, maybe identify that in the y direction, the momentums have to cancel and be 0. That's not an unreasonable thing to expect. We'll find second semester, we'll do a little bit more of this, and we'll see that there's some other things that happen. For example, in the elastic collision, this has to be a right angle. That's kind of how you play billiards if you know anything about playing pool. In real life, they don't have to be, though, right? Because there can be other things. Most collisions are not elastic. The thing about the homework is that you have to do all the stuff we just did and all the other stuff from the beginning of the year. So let's take a look at some of the things that are in your homework, shall we? One of your homework questions looks quite like this. A bullet strikes a block and becomes embedded in the block. How fast does the bullet have to be traveling so the block can do the loop without losing contact with the loop? This is one of your first homework questions. There's a lot to unpack here. but the problem is telling you where to begin. So do you understand what's going to happen? The bullet's going to hit the block, and the bullet and block are then going to move to the right. How many of you understand that part, that there's a collision? And then, of course, the bullet and block are going to move to the right, but they're going to hit the loop. In order for them to travel through the loop, certain conditions must have to be made for them to successfully make it through the loop. One of those conditions is that at the very top up here, we know that net force has to equal MAC. The only way the bullet block combination make it through the loop is if those conditions are met. And for those conditions to be met, the mass of the system plus the normal force has to equal mv squared over r. So assuming they gave us r, and they did, and told us about the bullet and block, that condition has to be met. Now, the normal force can fluctuate, but it can't be any smaller than what? Wow, that's just too bad. 0. It can't be any smaller than that. It can't be negative. If you want to maintain your contact with the surface, you have to have a centripetal acceleration that's greater than the weight. So you check your value at normal force going to 0. That condition has to be met. That's the minimum velocity the block must have to successfully make it through the loop. This is 2 units ago. Now, to get up there, the block has to have both kinetic and gravitational potential. Do you know that? Sounds to me like there's a conservation of energy question here, because they have to make it to here with the right amount of kinetic energy in order for them to successfully make it around this loop. This seems like a conservation of energy problem. So although I know the condition that has to be met for them to be able to stay in circular motion, they need to have enough kinetic energy here in order for them to actually make it through the loop. At the same time, that kinetic energy, the kinetic energy of that system, comes from the collision. The block had no kinetic energy before the collision. So there is a collision, and a collision is the instant before contact and the instant after contact. There was a moment right here where the bullet became embedded in the block and the bullet and block have a combined velocity. That's a collision. Here we're going to have mass of the bullet times the velocity of the bullet equals mass of the bullet plus the mass of the block times the velocity of the system. That's a conservation of momentum question. This problem has a conservation of momentum part, conservation of energy part, and a net force part. Let's look at another question you have in your homework. This is a ballistic pendulum question. The idea about a ballistic pendulum is that a bullet strikes the block. The bullet and block get joined together, and through being joined together, the system moves upwards until it comes to rest. It's called a ballistic pendulum. The idea is that you should be able to determine from the angle how fast the bullet was going. You guys see it? You get the idea of what's happening? Bullet strikes block, bullet and block have velocity. After they have a velocity, they swing upwards. It's very similar to what we just did. The thing that's missing is that there's middle ground here. When is this a conservation of energy problem? And when is this a conservation of momentum problem? Because it doesn't always conserve either. We know it doesn't conserve energy during the collision. So there is a part here in the middle. There's a part that's left out. The part where the bullet becomes embedded in the block and the bullet and block have a combined velocity, but they haven't started to move yet. Right? That's the collision. A collision occurs first. In this one, mass of the bullet times the velocity of the bullet is going to equal mass of the bullet plus mass of the block times their combined velocity, the velocity of the system. But now the system has kinetic energy. And because it has kinetic energy, it can use that kinetic energy to swing. But there's an external force acting on the system, right? Tension and the weight of the block. Together, that forms a system in which there's only a conservative force acting on the block, weight. That conserves energy. So over here, gravitational potential. So 1/2 m plus m v system squared equals mg, well, m plus m gh. And also your memory that h equals L times 1 minus cosine theta. You remember that too, right? All of this is what you have to do. This is all the things. It's all in your notes, or should be. There's more, of course, like what's the tension in the string the moment the bullet hits the block? That goes right back to net force equals MAC. Right? Circular motion the moment the bullet becomes embedded in the block. Make sure the string doesn't break. It's the fastest the bullet can be before the string will break if the string can only take so much tension. Ready for the next one? Just throwing out ideas here. We're not working them. I'm showing you how to work them. You will have to do this. And since many of you haven't started the homework, this is what you're up against. And I'm noticing you guys are just as quiet as the other classes. So there's this one. You'll like this one. This one's fun. Now for the coup de grace. Do you have an imagination of what's happening here? I release the block here. It swings downwards, has an inelastic collision with this box, and then continues to swing upwards here. Doesn't go as far. Does that make sense as to why? It was slowed down. Now, this part's important. I think conservation of energy tells you how fast the blue block is going at the bottom. But I also think conservation of energy tells you how fast it leaves the bottom. And those shouldn't be the same because it doesn't swing up as high, correct? Do you see that part? Because that part's important, I think. Because there's a collision that takes place there. Now, of course, knowing the height of the table and where the box lands could be used as well, right? Because this is a projectile problem now.